Hi everyone, this is Dr. Hawkins recording the next topic in a series of videos on some of our background information for our research. And as you know, most of what we do is developing deep eutectic solvents. So what I wanted to do was describe a little bit about what that means, because obviously that's not something that we cover in the curriculum in terms of general chemistry or organic anywhere in the undergraduate curriculum. So deep eutectic solvents, probably the easiest definition, the one I always use when I describe them to people, is the combination of two or more components is lower freezing point than any of its individual components. Okay, so if you put two solids together, or I like to think about it, if you put two solids together and then they melt into a liquid, that's something like a deep eutectic solvent. Now, of course, there are some caveats and there are probably better definitions, but I want to kind of start with this one. And what we want to see is evidence, so for it to be a deep eutectic solvent, you want to see evidence that we have freezing point depression beyond that of just merely an ideal mixture. And we'll talk about what an ideal mixture is in the next slide. And I also did want to mention, we call these deep eutectic solvents. We want to see this freezing point depression. For the most part in the literature, the term deep has kind of lost its meaning. Back in 2004, when Abbott first reported some of the initial deep eutectic solvent work, they were recording with the compounds were recording hundreds of degrees of depression of the freezing point. We oftentimes don't see that level of depression. So this term's deep, it's kind of a catch-all now. So anyway, but that's what that means. All right. So so this freezing point depression, I talked about an ideal mixture, and basically freezing point depression is one of the colligative properties. It's something we've covered in Gen Chem before, and oftentimes in physical chemistry, where the colligative property is just a property. It depends on the amount, not the identity of the solute. So it's not really something that we really like to think of as chemists. We like to know that the identity or the structure of our compounds or our complexes matters, right? That's what we do in chemistry. But colligative properties are one that don't depend on the identity. And the reason why is because a colligative property applies to an ideal mixture. And ideal mixtures are where basically the intermolecular interactions of the solute solvent and the solvent solvent are identical. So there's no net enthalpy change by putting a solute in the solvent, okay, in terms of an ideal mixture. But you still, in that case, even when you put those in, you do depress the melting point or the freezing point, and that typically could be referred to as a kind of result of the change in the entropy. So you have one entropy of just solvent-solvent interactions, and that has some kind of order. You put a solute in there, and now we have a different sets of states. So we have some solvents that will see solute, some solvents will only see solvent, and that changes the properties of the mixture. And so it's one of the classic examples of freezing point depression is if you live up here in the north where it snows and ice is on the roads, you put salt on the roads to lower the melting point of the ice so that it turns into water. And that's a colligative property. All right, so we can quantify the freezing point depression. Okay, so we can quantify this, how much we suppress the freezing point of this solid liquid phase change according to this equation shown here, where we have X is our mole fraction of the solvent. So depending on how much solute, that would be it's from 0 to 1, although below 0.5, one would argue that you would change which would be the solvent itself. But the mole fraction of the solvent, the heat of fusion of the solvent, so that's something you can typically look up. So of the pure solvent itself, R is our gas constant. The T fusion is our original melting point of just the solvent itself, and then T is our new melting point. So all of those are measured. The one thing you'll see in here is we have this gamma. That's an activity coefficient, okay? In an ideal mixture where we have suppressed or we don't have any, that the intermolecular interactions between the two components are identical, the activity coefficient is equal to 1. So a better definition of a deep eutectic is one where the activity coefficient is less than 1. And that results because you have strong interaction. So now we're actually going to have an enthalpy of interaction between our two components, our solvent and solute. And strong interactions, if you think about strong intermolecular interactions, the first thing you think is hydrogen bonding. And so oftentimes the language of the two components or the components of a deep eutectic take on the language of hydrogen bonding. So we typically will classify hydrogen bond acceptors and hydrogen bond donors, and we put them together. Now, if we go back to this review by Smith and Abbott from 2014, which I have the citation at the bottom, at that time he identified 4 different types of deep eutectic solvents. There probably is identified a fifth. And one of the types is an anhydrous metal chloride or metal halide with other kind of components and so forth. The most typical one, at least the one we use in our lab, is called type 3, and that's where we have ammonium chloride salts and your classic hydrogen bond donors. Okay, so we go and we'll look at examples. So hydrogen bond acceptor, ammonium salt. So typically the ammonium salt is a choline chloride, and show both the structures, and tetrabutyl ammonium chloride, right? So we have a little bit larger, more hydrophobic hydrogen bond acceptor in that case. And then a hydrogen bond donor is any classic hydrogen bond. We have an oxygen, a nitrogen, or a fluorine, although we haven't done any fluorine work here. So something like an amino acid, a carboxylic acid. So I show an example. Glutamic acid is one, and we've made deep eutectic solvents with glutamic acid and the hydrogen bond acceptors. Lactic acid is a carboxylic acid, and alcohol. So anything that is a hydrogen bond donor could typically form a deep eutectic solvent, or at least a type 3. All right, so what this does, so why do we study deep eutectics? What's so important about them? We can make these liquids, right? And they can be solvents just like water or hexanes. But since we get to choose what components are going into the mixture, we also get to tune or choose the properties of that mixture. Okay, so in other words, if we wanted a more hydrophobic solvent, for example, we might choose a more hydrophobic hydrogen bond acceptor. So for example, like the tetrabutyl ammonium chloride versus choline chloride would be more hydrophobic deep eutectic solvent. Or, as we typically do, and what we're trying to study is chirality, if one of the components is chiral, we can then control how it interacts with chiral molecules that we dissolve in it. So how does it discriminate between two chiral molecules? And there could be uses for that as well. And also the molar ratio. So we also get to control how much we put in to the deep eutectic solvent to control the properties as well. And so, as you can see, there's a pretty simple definition. The number of possible deep eutectics is very large. I've not put a number to it, but you can imagine any hydrogen bond acceptor, any hydrogen bond donor, and in multiple ratios could form a deep eutectic solvent. And that's just in the binaries, where you would have a large number of possibilities. But we could also start putting in 2, 3, so ternary combinations, quaternary combinations of components to suppress the melting point and control the properties that we want. So obviously there's still much to be explored in terms of the development of deep eutectic solvents, and we plan to do that.